Today's session is John and Matt. I'm sure a lot of you actually know them both. The session is going to be approximately 35 minutes long, and we'll have a Q&A at the end. We're going to record it, so if anybody wants to get a copy of the recording, we'll organise that for you. Obviously, we've got two superstars here, John and Matt. They're never going to say that. But John is a chemical engineer. He's been in mineral processing for 30 plus years. During his career, he was a group leader at Mount Isa Mines. John was also process control superintendent and process development superintendent at KCGM, otherwise known as the Super Pit. During his time there, he acted as the production superintendent and the mineral processing manager. He's also spent a number of years in oil and gas industry, and this is when he realized his passion was the mineral processing. And Matt graduated from Deakin University with a Bachelor in Applied Science Chemistry, focusing on the management of dangerous materials. He transitioned into PLA process analyzers, working in the ore processing field, focusing on the bed level measurement with the PLA SmartDiver system. So today's session is bed levels and metallurgy requirements for Thickener Control, and I'm going to hand it over to the experts. Yeah, so we'll do questions at the end, but so feel free at any point as you're going to put questions in the chat, and then we'll sort of field them at the end when John's done. Yeah, so over to you, John.
Or Matt. It was a first Matt.
I'm just going to share my screen. Yeah. Good one. So, welcome everybody, and thank you for joining us here today. Myself, Matt Smith. I'm from Precision Light and Air Process Analyzers, and John Karageorgos from MANTA Controls. This will be the first of what will be a series of webinars looking deeper into the operations of thickeners in ore processing. The next one will be on flocculant chemistry, but today's webinar on the metallurgical requirements for controlling thickeners. So the dewatering process is crucial for the for ore processing and mining, and involves sedimentation and consolidation of colloidal suspension. So while modern dewatering theory and models accurately predict lab scale batch settling tests, research by Crust says that predicting the full scale performance of gravity thickeners still remains challenging, with existing models underestimating thickener solids flux by up to 100 times. So with anecdotal evidence showing this to be true. But it's more than just beaching or the bogging of rakes that is of concern to us. So the way the thickener operates also affects the production and throughput. Now, it's commonly accepted that there are three basic solid liquid stages taking place in a thickener. You've got your free settling, the hindered settling, and the slurry compaction. Now, PLA have been measuring bed levels for over 20 years now, and we want to confirm our beliefs. Is there more to this? Which levels should we be looking at to help control thickeners better, and why? And that's why we're talking with John today. And we can see that for any thickener, there are a lot of processes going on inside the thickener, with only the two levers to help control the thickener: flocculant addition and underflow extraction rate. And this is where I introduce John Karageorgos, who will discuss these important aspects. Over to you, John.
Cheers, mate. Let me just share my screen, guys.
Go for it.
There you go. So I've got a few slides that I'll go through. I've also got a drawing board here, so I will be going through some hand-drawn pictures and writing. Plus, I've got two videos to show you as well. So as I flick through this, let's see if it all works properly. Come on. So MANTA Controls, we've been doing the relationship with PLA and MANTA stems about 20 years now, when I first met Nick at Murren. And we've been co-developing the diver over the years. There is a few other new models that have come out. Our core sort of control system is, some of you know, it's called the Cube system. We do have Cube lights for those who don't need all bells and whistles. Thickeners, we've actually spent quite a bit of time in terms of doing proper metallurgical training guides and questionnaires and that. And that's typically stemmed from some of the large mining companies. who, because there's a lot of turnover, they wanted additional training. So this sort of started about 15 years ago with some of the large miners. And happy to test your theory on what you know and what you need to learn about thickeners and why is that working. I was going to handwrite this, but I thought I'd just cut and paste some of our notes. So the first thing is, what is it you really want? The purpose. So when you're looking at thickener operation or thickener control, you want to make sure that it's safe and stable. So you're trying to create what is safe and then also a stable thickener. And the other key thing is you're trying to maximize throughput. You don't really want your thickener to be the bottleneck. And you could have a thickener in tailings, you could have a thickener in a pre-leach environment, or you could have CCDs or wherever you need to dewater. So in all those instances, you don't actually want the thickener or CCD or washer, whatever you call it, to limit throughput. You want it to be able to push tons. And by doing that, you also want to maintain the highest possible water recovery or liquor recovery, if you're in a CCD washer environment, which also means a thicker underflow density. So you can think of them either way. And whilst doing that, you want to also make sure you're adding the right amount of reagents, which is flocculant or coagulant. Because if you're overdosing with flocculant, as some of you might know, it's a nasty chemical. It makes the bed go gooey, and you're running at higher rate torques unnecessarily. If you're into slimes thickening and you need to add coag, the good thing about coag is that there's no detriment to the rheology of the slurry. It's just going to cost you more. So coag's quite nice to work with because you can overdose and it's not going to affect the circuit, but it just is expensive. So the purpose is to push tons, have a stable thickener, have a safe thickener. We'll talk about what safe means, at the highest possible liquor or water recovery, which means the highest possible underflow density, and to not waste reagents, which is coagulant and flocculant. Cool. All right, let's use the little clicky button. Now, what I'm going to show you is, this is some before and afters. This is what you're trying to achieve. And then we'll go through how do you actually achieve those. So here's a thickener. Some of this data is from a Goldfields plant. I'm allowed to show this. This has got general control. So here's the underflow density down the bottom right. You can see we're averaging. I had to normalize the numbers, so these numbers aren't real. These are just fake. It's more to look at the trend. That's how I'm able to show the data. And we're running back then at bed pressure and rate torque. One thing with rate torque is that we do a lot of thickeners, and most operations, operators, even young mets are scared about rate torque. Thickeners are designed, just please note this, you can go check it with your thickener manufacturer. Thickeners are designed to operate at 40% rate torque day in, day out for the service life of the equipment, which is 15 or 20 years. There is nothing wrong, therefore there is nothing wrong with running rate torque at 40% consistently. Nothing wrong with that. Our hardest run thickener is actually at Prominent Hill, where we're running at 55% rate torque, and that was done on purpose because we needed to dewater. And I'm going to show you some of those results as well. So here's a general running thickener. Then when we go through the metallurgy of thickener and actually start looking to control it better, we should be able to get a more stable and a higher underflow density. And to achieve that, then we're running higher inventories into the thickener, and we're also working the thickener a bit harder. So you might be running at slightly higher rate torques. Yeah. Other numbers to this came from Prominent Hill. This is, again, we can publish this. General control, these are real numbers. General control, they were running at around the 64 mark. They needed water. So this plant actually needed water because without water, they couldn't push tons. So we're in a catch-22. So the focus was on the back end This is on a tailings thickener, which then we're able to recover more water so we can actually push tons. So it's sort of a catch-22. So by doing things a bit better, running a thickener better, we're able to get an increase in underflow density. And on the flocculant, this is just purely flocculant, and this is now like a signature. We're able to reduce flocculant by quite a bit. So they're overdosing. And we'll talk about, you know, how do you know how much floc to add, and then how do you increase the what actually really drives the percent solids. So that's what we're chasing, and we're doing this at maximum throughput. And this curve here actually shows you something. You'll see there's a curve in this, so you see that soon. Cool. All right, so back to the original purpose. Now, before we start, we're working in minerals. Doesn't matter what it is, you know, base metals, copper, lead, zinc, gold, platinum, lithium, it doesn't matter. Nickel, it doesn't matter whether it's a clay, whether it could be a bauxite, it doesn't matter. It's all minerals. So when we start to look at minerals, we have to look at things on a size by size basis. And so you need to know what the sizing curve, what the particle size distribution is for the feed coming to the thickener. Because what happens is the difficult particles are the finer particles, and strange things start to happen on fine particles. So, and the approach that we take is we segment each size fraction to sort of understand what is going on with each size fraction. Because when things are running well, things are running well. But it's not good just to sit there and go, oh, everything's cruising. You still want to make sure that the size fractions are behaving the way you want them to. Because when things don't behave well, that's when you interrupt the tons through the plant, or you might even have issues with the thickener where you have to reduce throughput. And that's a lot of money that's been lost. So it's really important to get your sizings and then be able to size correctly, and then try to understand the behavior of each size fraction. So I've got a cyclone overflow, cyclone survey here, where we might be sending overflow to a thickener, might be a slime thickener. We might be sending coarse, might be to a paste thickener, where you might be getting a cyclone underflow, or you might bypass the cyclones entirely and go direct, you know, the feed. After the recovery stage, you grind, you recover, whatever that may be, spirals, floats, leaching, and that size distribution goes in. So I can't emphasize more. You need to know what size distribution you're sending to the thickener. The other thing you need to know is you need to go to the lab and get your thickened, you need to do some settling tests, or you can actually grab this from your thickener underflow, and you need to learn the relation between viscosity and percent solids. And the reason for this is each ore type, each mineral type will thicken at its ultimate density, and they're not going to be the same. So there's no way that I can get a nickel laterite to thicken to the same as a copper sulfide. There's no way. And the problem with viscosity is, well, this affects pumping. So we have thickeners that are pumped, the underflow is pumped, and some thickeners it's gravity fed. So as you thicken, depending on the mineral type, it's really important to know your viscosity density trends, because if you do thicken to a certain point, you might start to find that pumps are struggling. Centrifugal pumps struggle about the 80 mark, and that's why you can see this is real life data. You can see that there's a lot of data down here, and then there's only a few little data points where we're doing test work, where we're pushing the density up, increasing viscosity, having pumping issues, and we're lucky in this plant to have hot process water to try to change the rheology to be able to pump. So these are really important. So sizings and understanding your rheology curves. All right, cool. I'm actually used to a bit of banter, but this is something we'll do questions later on. So to achieve this, there's actually 3 things that you need to do. There's actually 3 things. So what I've written here is, I might actually go to my whiteboard just for the moment. Let's do an escape here. And I'll go to page 2. I'll move that out of the way. Move that out of the way. Go to page 2. So page 2, so there's 3 golden rules to come on. Sorry, this is in the way. There's 3 golden rules to be able to obtain the density you're after, and pushing tons and minimizing flocculant. So the first one is you need, I'm just writing the way I talk, you need to have a method to add the right amount of flock. Correct amount of flock, let's say, that's probably a better word. Oh, flocculant. Now, most metallurgists, I'm a chem eng / also metallurgist. If we don't know, we start to mass balance things, and we're going to get it wrong. So anyone who tries to mass balance, more than likely, you're going to overflock, more than likely. So you need another method. The other one is you need to leave, and I'll show you some slides in this one. You need to leave the particles. Oops. Where's my particles? In the thickener as long as possible. And we'll talk about what that actually means and why. Chicken scratching, as long as possible. This is really important as well. The other one is you need to dilute the flock, you need to dilute the feed. And this is something that you can actually do. We'll talk about it today. This helps settling as well, the flock. So you need to know that you're diluting correctly, and the feed. And lastly, what you can't do, anyone who tries to control a thickener by purely using the underflow density, that's incorrect. So you can't control density directly. So that's a no-no. So they're the directly. So the first 3 are our golden rules, and the 4th one's a no-no. So if you do this, and you do this, and you do this correctly, and you don't do this, you're going to, the thickener will be set up to dewater the whatever feed's coming in at whatever rate at what it's able to do. If you do this, you're actually truly starting to optimize the thickener. So let's have a look at one of these 3. So the first one is, can you see that? Let's just go full slides. So the first one is, this ties in with the viscosity curve. So if I had another curve of another ore type, say a clay ore, it wouldn't thicken to the same as, let's say this is a sulfide ore. And what you're trying to do is you're trying to leave the solids in the thickener for as long as possible, because that's where you're getting compaction and let's call it resonance time. And as it compacts, the density starts to increase until it reaches ultimate density. Now, if you're sitting here because of throughput and you start to push tons, well, you're going to come down this curve. And if you have a look, if you remember, look at that shape of this curve. If I go back to this one, you can see that we're actually moving up the curve. And we now go a little bit higher, but there's a point where you can't go any higher because that's the limitation of the thickener itself. So I think that's pretty cool. You can actually see it in real life data. There's also something else that happens with leaving the thickener in the particles in the thickener for as long as possible, but that's for another discussion, because then I'll spend another half an hour talking about just that. The rakes actually do something to the bed as well, but that's another discussion. So leave the particles in the thickener for as long as possible. Okay, and here's some data to prove that as well. So we're using, in this one here, everyone's got bed pressure. You're trying to find, where the solids are in the thickener. I've got just generic data here. So you can see that as we increase inventory in the thickener, so you're trying to increase inventory in the thickener, and as long as it's safe. So we're now compacting the density relationship with two different ore types. Follows the same trend. The longer I leave the particles in the thickener, the higher the density I'll get. And I think most of you would have seen that as well. So there's some real life data on that. So that's point one. So point one from where I wrote was leave it in the thickener. All right, where am I going to next? I don't know where I'm going to next. The next part was, how do I know how much flock to add and then also dilute? So I thought, let's just run through some videos. Let's run through some videos. Where are they? Let's see what we're talking about. So to really understand what's happening in a thickener, the measuring devices that we've had, the old float ball on a stick, submersible ultrasonics, calorimeters, all those devices, none of those really work when you start to have particles that aren't settling properly. And that's when you want to know what's going on. In the old days, especially at KCGM, Mount Isa days, we used to joke about putting on our snorkeling gear and getting to the thickener and having a look to see where all the particles were, the various interfaces. And that's where the diver came into play. And what we have here is a video. Oh, that video can stay over here. So here is a diver. This is one of our versions. So we're just going to watch a video just to show you. So what you have is, all you're doing is, there's a sensor on cable, and it's wrapped around a drum, and the drum just lowers the sensor into the thickener. So what we're doing is we're measuring the density profile of particles settling inside the thickener, and we just go all the way to the bottom of the thickener. So we're lucky enough to have a video during commissioning of a thickener that was empty, and let's just watch it. So here's the sensor. You can see it. It's lowering. It's coming down. We're missing the rakes. You have to get all that correct. And as it's dropping, we go to about 0.5 meter. We call it clarity hold. You need a stable reading. You see it stop soon. But while it's diving, we're just measuring the density profile, which is known as interfaces. PLA they use the word beds. MANTA uses more interfaces. The compacted zone, PLA calls it heavy mud because they've come from alumina. MANTA calls it compacted bed because that's what we do. So as we're diving, because I'm not sure if some of you probably haven't seen this. Those who've used these before know this. I know some of you commission these. So we're still diving. And the rakes are, the rakes also, anyone who is into rakes, the important thing about rakes is the tip speed. The tip speed should be moving somewhere between 8 to 10 meters per minute. Anything slower, it's too slow. Anything faster, it's too fast. So here we go. As I've been talking, we're diving. And while we're doing this, we're measuring the interfaces. And it's these interfaces, and I think on the current diver mat or sub, we can easily get at least 5. I think we can easily get 5. So here we go. Still haven't reached the bottom. Here we go. And then it reaches, bang, and it retracts. And that's one set of reading. It'll come up, give itself a good wash. You'll see the sprays turn on. You can see here, this is a submersible ultrasonic. They're a good idea if you're on a fishing boat fishing with seawater and sand, but not in a thickener. It just doesn't, we haven't had those working properly ever. And here we go. It's coming up. It's coming up. Coming up. It's coming up. It's coming up. It's coming up. And the spray is going to turn on soon. Give a nice wash. And then what rating? Then we're waiting for the next rate to pass. We're monitoring where the rates are. This is a long arm, short arm. There's the sprays. Wash and you can spray whichever way you want. So that's, I thought I'd show that just to show you what actually happens with these analyzers. So I'll stop that. And there's another video I'll show as well. But what we get from that is this. Oops, I've got my red mark there. Sorry, that's my pen. These are two interfaces. You can get up to 5. So, and these interfaces are like MANTA traditionally uses various gram, we call it gram per liter. So the relationship between these interfaces, if I had all 5 running, whatever they may be, when particles are settling really well, they're close together. When particles are not settling really well, they become separated. So you can use that information to then use flocculant to manage how these interfaces separate. So you can see here, and this is through a whole day, and this is dynamic. And this is the size, the particle sizes, the size distribution changing through the operation, even through a day, hour by hour. So you can see here, nice and tight, we're actually settling really fast. Over here, we're slower. So there's a little bit of, if this is a sulfide ore, which it was, there could be a little bit of talc, a little bit of clay coming through during this time, and then we'd start to up the flock dose in this point here. So over time, you'll learn how the interfaces should respond, and you're also trying to get them reasonably stable, and that's not too bad. A nice stable period. You know, that's about night shift ran quite stable there. This is actually a stable operation. So knowing how those interfaces react, you're able to then use flocculant to maintain those interfaces to whatever you want. Some sites even, you know, we start to worry because this is depth. We use depth, zeros at the surface, and some sites were allowing the interfaces to creep up to, you know, in this one here, 1.5 meters, 1 meter. We will not go typically anywhere near above 1 meter below the surface. Some sites we keep them down to 2.5, depending on what it is. So that's really important. And this information you just can't get accurately and repeatedly from any other analyzer at the world at the moment. So that's really important. And without that, then you're back to your mass balancing your flocculant. You're going to be overdosing, which is going to cause you to have higher rate torques, which means you're going to suck the thickener out, and then you're in a mess as well. Cool. So next one, click on this. Oops, wrong slide. Okay, wrong slide. I'll show you another video. This is now flocks forming. I've got to move this out of the way. These are really cool. So this is an old chlorometer. I use it because I actually like you can see that this is an online settling test. You'd probably do this in the lab more, but if you watch this, let's see if I can make it bigger. You'll start to see the flocks forming. I don't know if anyone's watched it. And what you'll see here is you start to actually see, this is like your clear zone, and then you start to see your interfaces. And then down the bottom here is more of the compacted bed, if this was an entire thickener. Now these devices, they need a lot of maintenance to work. And the problem with these is the sample. But the really cool thing about these is you can actually see the flocks. And so these flocks are actually going to be forming inside the thickener. And it's knowing, you know, being able to measure where the particles are settling. You can actually see that the start of settling is around here. And then once the flocks are formed, all they're doing is falling down. And there's probably no more you can do to the flock at that point, apart from letting it, you know, sit at the bottom and then just gently compact. And so the longer you can leave the compacted, the flocks at the bottom of the thickener, which is residence time, then they're going to compact and you get a decent underflow density. The rakes also play a role, right? There's something else the rakes do. So leaving the flocks to form the bed in the thickener as long as possible also allows the rakes to do something to them, which then gives you a nice density. So it's being able to measure these interfaces is really important. So we're back to achieve decent thickener control. You need to know how to add the right amount of flock. You need your interfaces, and at the moment, the diver type instrument, the diver sub, we have another one called the sub, is the only thing in the world that we know that does this consistently, day in, day out. If there was something else that was better, we'd be using it, right? And Matt would be selling it. So to do number one, you need these interfaces. You just need it. The other part is to leave the particles in there as long as possible. You can also use your interfaces to do that. Plus, you might have bed pressure, and then it's learning the relationship between what bed pressure means for the interfaces. That takes a little bit of logging data and doing a bit of analysis. We have our own methods. And the other most important thing, which I'll wrap up, is diluting of flock. So with flocculant, and I'll just do a quick 30-minute sketch. Actually, I can do that here. If I have a, here's on, and you can all go and do this. Let's go back over here. Sorry, number 3. You can all get a measuring cylinder, go to your thickener feed well, get a sample, and chuck it in the measuring cylinder, fill it up, and you'll have particles, and they'll be trying to settle, right? Lots of particles. Give it a mix, put your hand on the measuring cylinder, fill it up with feed, swish it up, mix it up, and just watch it settle. You'll see the particles settling at a certain rate. Then if I then mix it all up, pour half out, go to my overflow, get some overflow water, and then dilute my measuring cylinder, I'm now diluting not only my flock, my feed as well. I now have less particles in the same volume, and these are going to settle faster. And you can see the reason why is if I don't dilute, I'm causing traffic jams, hindered settling. Whereas what I'm trying to do is allow free settling. And so the more there's a certain dilution, which is optimum, which you have to find doing test work. And this is critical as well. So those who've got your Autotech thickeners, the old Superflow design, you're using dilution ports, make sure they're clean. You might have a turbo dual submersible pump diluting. There's history to dilution. You might be running the old IMCO, FLS Schmidt, IMCO, GL&V thickeners. They're using the Venturi principle. Make sure your E-ducts and all that stuff is really clean. So by doing those 3 things, where are we? Number 2. You need to have a method to add the correct amount of flock interfaces. You need to leave the particles in the thickener as long as possible. Bed pressure interfaces. You need to dilute the flock and feed so you don't get hindered settling. You do those 3, and then the outcome is the best possible underflow density, which is the highest water recovery. And I think that's 31.5 minutes. So this is a very brief chat, and now I suppose we're open for questions. If anyone's got any questions, we can go through those.
Perfect, John. Yeah, that was excellent. Yeah. So thank you.